Have you ever stood and watched a river during a huge storm, just swelling and rushing by? Well, that incredible flow of water isn't just random chaos. It's actually a signature, a totally unique story that the landscape itself is writing in the water. And today, we're going to learn how we read it. And it really all boils down to this, right? You've seen it. A sudden downpour turns a city street into a raging torrent in minutes. But you can go out into a forest after that same storm, and the ground just seems damp. It's like it soaked it all up. The answer to that mystery is at the heart of what we're talking about today. So here's our game plan. We'll start with what a river's storm signature actually is. Then we'll break down its anatomy. After that, we'll dig into nature's own recipe for how rivers respond, and then see how our concrete footprint completely rewrites that recipe. Finally, we'll tie it all together and talk about why this is so critical for our future. All right, section 1. To really decode what's happening during a storm, scientists have this amazing tool. You can almost think of it like an EKG for a river, a heartbeat monitor that tracks exactly how it reacts when the skies open up.
And that tool is called a storm hydrograph. Now, don't let the name intimidate you. It's just a graph, but it is incredibly powerful. Along the bottom, you've got time, and going up the side, you have the river's flow rate, what scientists call its discharge. It gives us this perfect visual, this picture of how a landscape, whether it's a city or a forest, handles a ton of rain.
So now that we know what it is, let's pull this thing apart and look at its anatomy. Every single part of this curve, every rise, every peak, every fall, tells a crucial piece of the story. The story starts with the rising limb. This is where runoff from the rain starts hitting the river, and you see the water level begin to climb. That climb leads us to the peak discharge, which is exactly what it sounds like, the absolute highest point of the river's flow. But honestly, the most important character in this whole story is the lag time. That's the delay between the heaviest rainfall and that peak flow. After the drama of the peak, the falling limb shows the river coming back down. And way down at the bottom, that steady line is the baseflow, the river's normal, chill state just fed by groundwater. So these hydrographs tend to have two very different personalities. Over on the left, you've got the flashy one. It's spiky, it's sudden, it has a dangerously short lag time and a really high flood risk. Then on the right, you have the subdued hydrograph. It's a much more gentle, rolling curve with a nice long lag time and a much, much lower risk of flooding. The whole game is figuring out what makes a river one or the other. So what is it? What determines that shape? Well, let's first look at nature's own recipe, starting with the raw, natural ingredients of the landscape itself. First up, what's under our feet? The geology. You can think of porous stuff like sand or chalk as a giant natural sponge. When it rains, the water soaks right in, travels slowly through the ground, and trickles into the river gradually. That gives you a nice subdued response. But non-porous materials like dense clay or solid granite, they're like laying a sheet of plastic over the ground. Water can't get in, so it just runs right off the surface and makes a beeline for the river, creating that flashy, dangerous response. Next, the shape of the land, the topography. And really, this one is just about good old gravity. On gentle slopes, water moves slowly. It has time to meander and soak into the ground, which means a longer lag time. But on steep slopes, forget about it. Water picks up speed, rushes downhill, has zero time to infiltrate, and slams into the river channel all at once. That shortens the lag time a lot. Even the overall shape of the river basin matters. It's all about timing. If you have a long, stretched-out basin, water from the far-off streams takes a long time to get to the main river. It all arrives at different times, spreading out the impact. But in a more circular, bowl-shaped basin, all the streams are about the same distance away. That means all that rainwater can arrive at the same spot at pretty much the same time, delivering a single, powerful punch and a very flashy peak. And finally, we can't ignore what was happening before the big storm. If it's been raining for days, the ground is already soaked. That natural sponge is full. So when the next big downpour hits, that rainwater has nowhere to go but sideways, straight into the river. This can turn a normally subdued landscape into a very flashy, high-risk situation, real quick. Okay, so that's nature's playbook. But here's where it gets truly wild. We humans can come in, take that natural recipe, and completely rewrite it, often with much, much more extreme results. And this takes us right back to that first question about the city street versus the forest. Urbanization is the ultimate game changer. We pave over that spongy soil with concrete and asphalt, impermeable surfaces. This means zero infiltration. None. Instead, we build storm drains and channels specifically designed to get that water off the streets and into the river as fast as humanly possible. The result? An extremely flashy hydrograph, a terrifyingly short lag time, and a huge peak flow. That is exactly why our cities flood so fast. Another way we have a massive impact is through vegetation. When we practice deforestation, cutting down forests, we get rid of that amazing tree canopy that catches the rain and the root systems that drink it up. More water hits the ground and runs off, creating a flashier river. But, and this is the hopeful part, the reverse is also true. When we plant trees, afforestation, we add that protective, thirsty layer back. We slow the water down and help create a safer, more subdued, and healthier river signature.
So, a lot of science, I know, but why does any of this actually matter in the real world? Well, being able to read these river signatures isn't just an academic exercise. It has huge, real-world consequences for every single one of us.
This chart really brings it all home. Look at the patterns. Clay soil, steep slopes, deforestation, a circular basin, and especially urbanization. What do they all have in common? They all decrease the lag time. And the key takeaway from this whole thing is this: a shorter lag time always, and I mean always, equals a higher flood risk.
And that is why we read these signatures. It allows us to predict and manage floods, which saves lives. It helps us design smarter cities with green infrastructure that works with nature, not against it. It helps us understand the true cost of cutting down a forest or building a new subdivision. It's about protecting our water, our ecosystems, and preparing for a future where our climate is changing.
Which leaves us with this final thought. We know how to read the story that our rivers are telling us. So the real question now is, as we continue to shape our world, how will we choose to rewrite that story? Can we use this knowledge to work with our landscapes and create safer, more subdued signatures for all the rivers that we depend on?